Well, thank you very much. And I'm delighted to be invited to give this Capstone to Vis 2023 and really honoured. And I must say, what a kind of wonderful community. I've been made to feel incredibly welcome. And I think that speaks volumes about this community. So I'd like to begin in the way we usually do in Australia by acknowledging the traditional owners of the lands on which we meet. Unfortunately, my clicker doesn't seem to be doing anything. There we go. And I'd like to acknowledge the people of the Woiwurrung and Boonwurrung language groups of the Eastern Kulin Nations, on whose unceded lands we're all gathered, and respectfully acknowledge ancestors and elders past and present. And I'd particularly like to pay my respects to any Aboriginal or Torres Strait Islander people here today in the audience. And I'd also like to recognise Lou Bloomer, who designed this wonderful artwork. And Lou's an Indigenous Bundjalung woman with an Iowan and Kamilaroi ancestry. And this work, thank you very much, this work aims to draw an analogy between the pathways in the lands that we walk every day and the pathways that we forge through life, which I think is a lovely idea, particularly as someone with an interest in geographical information. And in fact, this artwork by Lou Bloomer means a lot to me in particular because she designed it especially for my book. I'm a geographic information scientist and author of one of the main textbooks in GI science. And in fact, the third edition was published just a couple of months ago. Now, I would normally refrain from spruiking my own book at a talk like this, but in fact, we managed to get 5 of the 10 chapters free and open access. Including, in fact, the chapter on cartography and visualization. So feel free, that link should take you to the free chapters. And so anyway, this book was naturally front of mind for me when I was thinking about how to approach this talk. And what I chose to do was focus on the interdisciplinary nature of working in a field like GI science. It's an inherently applied field. It combines expertise from all sorts of different areas, not just computer science, which is perhaps more my background, but cognitive sciences and physics and engineering and geography and maths. And of course, design and visualization is also a key part of that. And I think there's actually a bit of a paradox that to me lies at the core of all of these interdisciplinary subjects like GI science. On the one hand, we need to have a clear expertise. I mean, after all, what's the point of a field, an academic area, if you can't point to your expertise? But at the same time, we need to be inclusive of ideas and actually bring in ideas from all sorts of other areas. So that was really the genesis of the title, All Over the Map. It's not just because I'm a geospatial scientist, so I like maps. You're going to see lots of maps today. But it's to frame that paradox, that sometimes we say, all over, like I'm all over it, meaning that I'm like really expert in it. But also the phrase, all over the map, sometimes gives that feeling of sort of chaos and not particularly expert in anything, just sort of cherry picking all sorts of ideas. So my hope is maybe that also resonates with people here in the visualization field, in the Vis conference, because I've seen an awful lot of really excellent interdisciplinary work. And I'm hoping that this is a sort of shared experience for people who work in interdisciplinary areas. But even if not, I've got some nice maps to show you at least. So over the years, I've thought quite a lot about what that expertise is for a GI scientist, what it means to be an expert in GI science. And I really came to the conclusion that fundamentally it's about these 5 key areas. I think GI science does come with that expertise in design, and particularly in cartography. I would count cartography as part of GI science, and there's a long history and tradition of design there, and also more recently in geovisualization. I think this is combined with an expertise in the structure of spatial information. What makes spatial special, we often talk about. And that means things like autocorrelation, that near things are more related, and statistical non-stationarity, that there's no average place in geography, and scale, that the more you look, the more you see in geographical information. I think the third area is uncertainty. I think GI scientists are often quite expert and nuanced in dealing with concepts like inaccuracy and imprecision and vagueness. I think we have expertise in spatial cognition, in kind of how humans think and reason about space and the particular ways that humans have evolved over millions of years to interact with space. And finally, the fifth area is, I think, dynamism in dealing with change and events, because, of course, the world is never static. And so that's also, I think, part of that expertise. And in fact, I did do a little bit of work a few years back trying to back this up with a little bit of actual data. And I looked at the occurrence of keywords related to those 5 expertise areas in different journals in particular related to GIS and GI science, but actually over a number of areas. And what this shows is all the different journals, or some of the different journals that I looked at on the left-hand side, but then the proportion of articles in those journals that had at least one of those terms related to at least one of those keywords as a focus. And so essentially what you can see is that the GIS related journals do tend to occur pretty high up. They tend to have high proportions of these sorts of terms. So IJGIS is the International Journal in GI Science. It's kind of the flagship journal for the field, and over 3/4 of the articles there a couple of years ago, when this data is from, have clearly related to at least one of those 5 areas of expertise. And if you look at the other end of the spectrum, AER is the American Economic Review. It's kind of the flagship journal for economics, and it has much lower levels. Now, it's interesting also that I think several other journals that are not necessarily kind of regarded as core GI science journals still occur high up there. In particular, for this community, the IEEE Transactions and Visualization and Computer Graphics also has quite high levels of some of these terms in there. And in fact, if you look into it a little bit more, there's still a little bit of a difference. So what I was showing here is for 4 selected journals, the proportion of pairs of terms that co-occur in relation to particular journal articles. And I guess what I'm hinting to you is that the GIS ones in the yellow and orange over on the right-hand side tend to have quite an even distribution, if you like, that all of the pairs are kind of represented. If you pick any pair of those terms, there's a reasonable chance that you'll find them. Whereas in some of the other journals like the IEEE Transactions, actually they're quite clustered, and you tend to have a sort of different fingerprint. They tend to be, in this case, you can look into the paper if you're interested in the detail, but they tend to be quite lower in the uncertainty, and as you might expect, much higher in things like visualization. So anyway, I don't want to labor that point, but I guess what I'm sort of suggesting is that expertise, certainly in GI science, maybe this is true for visualization as well, is not just kind of a single area, but it's really at the intersection of multiple areas. It's that kind of union of different ideas that I think underlies the expertise. So what I'm going to do in this talk is really go through those 5 areas and show you a nice map that I particularly love, that illustrates some of those ideas, and tell you a little bit about that what I see as that expertise. So here is my first map. It's a vegetation map. In fact, it's a rather famous one from 1869. I actually have a framed copy, a 1967 copy of it on my wall. It's quite big. It's sort of over 1.5 meters, or almost 1.5 meters across. And in fact, I'm going to invite you, if you like, to have a look at it yourself. So the maps, all the maps that I've done today, there's a little QR code, and you could also, the link should take you there if you need it. And that should take you to a zoomable version of it. So you can, my hope is that as I'm talking, you'll be able to kind of look around it and zoom in and see some of the details. So the map's called the Everett map because it was compiled by Arthur Everett in 1869, and it's the first ever forest vegetation map of Victoria. And I can't help, every time I see this on the screen or on my wall, but really be stunned both by its elegance as a data graphic, but also the sheer volume of data in there. I mean, when you zoom in, it's just stunning how beautifully, how much data's in there, how beautifully it's been presented, with what artistry. And also the enormous technical challenges of doing something like this is pretty awe-inspiring. Even today, with all of our kind of mapping technologies and satellites, imaging sensors, positioning, GIS, spatial databases, doing something like this is a major undertaking. Millions of dollars and many person hours go into that sort of thing. So being able to do it in 1869, I think, is pretty awe-inspiring. The map shows 12 vegetation classes. Almost 90% of the state was forested in 1869. Today, only about a third of the state is forested. So that sort of frames, some of the big environmental changes in the context of today's climate crisis. But the map also frames a very particular view of Victoria. It's a European's view, a colonizer's view. The Europeans arrived in Victoria in about 1800. But really, colonies started by Europeans in about 1830, and there followed 20 years of brutal conflict and subjugation of Indigenous Australian inhabitants. So this is a very European view, a colonizer's view, a conqueror's view of what's in Victoria and what matters here, and it's to the conquerors. And it doesn't say anything about 60,000 years of Indigenous Australian history. Even though it was 12 years after brutal massacres that totally changed, displaced Indigenous people off their lands and destroyed or irrevocably altered the ways of life of Indigenous Australians, and violence and dispossession that still echoes today for Indigenous Australians. So I think I approach maps like this, many maps of this era, with kind of mixed feelings of awe and discomfort. Awe in just the beauty, the data density of this sort of, and the technical challenges that had to be overcome, but also that discomfort in their history and the history that they erase, and how they not just convey meaning but create meaning. But I do think that, my point here is that maps like this do also underline that history of design in cartography. It's a really strong history, I think. And that's really at the core of part of this first area of GI science expertise of sort of cartography. And I think, the key part of that is the expertise in managing complexity, in being able to take vast amounts of data and display them in a way that's actually useful. And I sometimes illustrate this. Unfortunately, my clicker's not working again, so would you mind advancing to the next slide? I try and I like to illustrate this with this idea of abstraction. We've got an orthophoto, an aerial photo here, and a topographic map, and the orthophoto is essentially an aerial photo, but with the geometric properties of a Cartesian map. And of course, today we've got the technology to be, taking an enormous amount of this sort of imagery. It's much more up to date than the map. It's more detailed. It's more realistic. So the question is, well, why don't we just use these orthophotos rather than, worrying about maps? And of course, the answer is that it is the selection of information. It's what you don't show that's important in the map, rather than what's actually there. It's that selection process, abstraction, choosing which features to show, how to represent them in an understandable way, simplifying the depiction, that I think is at that core of cartographic expertise. So my second area is connected with the structure of spatial information. And I chose to illustrate this with the Pottinger map. And again, there's the QR code, so feel free to have a look at that one and zoom in and have a look at a bit more detail. This map's actually a 13th century copy of a 4th or maybe 5th century map. And the map itself depicts a world that includes features from the 1st century, or even clearly from the 1st century. For example, Pompeii's on this map. and that was destroyed in 79 AD by the Vesuvius eruption. It's centered on modern-day Italy, but shows Europe and parts of North Africa and the Middle East, and it's essentially a roadmap, showing routes and itineraries and distances between locations around the Roman Empire. So there's this rather wonderful mystery around how it came to be and who created it and for whom. It's over 6 meters long, so it's certainly not practical as an actual travel map. And I especially like it because it shows that it's not concerned with the geometry of the world. It's all about that connections. It's all about the topology of the world. And we think of transport maps, that like the maps you may have used while you're here in Melbourne, or the kind of the classic Harry Beck London Underground map. We think of them as very modern, but in fact, they're a really ancient idea. And for me, as a GI scientist, coordinates are actually the add-on, if you like. The structure of spatial information is really all about the relationships between places, like connections and containment and things like that. So coordinates are just one type of spatial information, but we're really interested in those connections more. So there's no attempt at geometric faithfulness here. It's all about the connectivity, and there's actually no need for geometric faithfulness. That's not necessary for the map. So as GI scientists, we frequently omit that sort of thing. Other examples of some of that spatial structure, I mentioned scale earlier, and the point here is that when you look at different scales, you expect to see different things, so that it's not the same things represented, for example, on a map at different scales, because there isn't a need to. The same features are just not relevant at different scales. And an understanding of that spatial structure arises in many different areas. These are choropleth maps, area value maps. It's actually two of the same spatial regions. This is the boroughs of London in the UK, and the data is fundamentally the same. It's the carbon emissions from a few years ago by London Borough. And the only difference between the two is the way that they've been classified. They're both two standard classification techniques. One is equal interval, picking kind of numerically equal bands, and the other is quintile, picking bands that have essentially roughly the same number of instances in them. And you get very, very different pictures, both of the overall levels of carbon emissions, but also the pattern of carbon emissions. So these, I think, are some of the things that as a GI scientist, you're very aware of and alert to. And I'll mention one other one that comes up a lot. Many of you may be familiar with this, the modifiable aerial unit problem. And this essentially frames the idea that when you're dealing with these sorts of area value maps, where you've got aggregation of information by areas, the areas themselves have a defining impact on the patterns that you see. So I've tried to illustrate this with some dots. These are the actual things that we're measuring, the red dots with the white borders. And I've placed a grid, a very simple spatial structure for areas, 9 spatial areas over there. And on the left-hand side, when you add it all up, you end up with a picture of very even distribution. Every grid cell has kind of one dot in it. But all you need to do is take exactly the same grid, exactly the same dots, and just twist it a little bit. It's about 15 degrees, and suddenly you get a very uneven picture of the distribution. So these are the sorts of things I think GI scientists are particularly alert to. So my third topic, it was uncertainty. And for this topic, I'm delighted to have permission from the Australian Institute of Aboriginal and Torres Strait Islander Studies, IATSIS, to show this very famous and important map. And again, feel free to have a look on your devices and zoom in at some of the detail. IATSIS is the Australian Commonwealth statutory authority for providing leadership in the curation and care of Indigenous cultural heritage. And this map was created in 1996, designed as a visual reminder, just a visual reminder of the richness and diversity of Australian Indigenous history and Indigenous Australia. So particularly if you're not from Australia, you might not be aware that there's at least 250 distinct Indigenous languages represented across Australia before European colony. And this map kind of gives you a representation both of some of the regions and some of the Indigenous nations and the locations of approximate locations of some of the different languages and language groups. And yeah, as I say, feel free to zoom in. I did also check with IATSIS that this was okay with them to display it in this way, because part of showing a map like this is that it's sovereign property of the Indigenous people, and so a condition of showing it is that we're very clear about exactly why we're showing it, and it's shown in the representation that it's provided in. It's expressly forbidden to sort of use this data in different ways. Doing so would be a breach of data sovereignty. And if you zoom in and have a look at the detail of some of the regions' boundaries, they're deliberately blurry, so they fade into one another. And that's because uncertainty is an intrinsic part of this information. It's, crisp boundaries are very much a European, a colonial construct. They rarely occur in the world, and indeed they crisp boundaries absolutely support a colonial worldview, where we're able to apportion land and assign ownership to it. So that's kind of part of the reason that IATSIS are very careful about how this map is used. And there is a long history, not only in Australia but around the world, of non-Indigenous colonists using data, and particularly map data from Indigenous people, for purposes that are actually not in those First Nations interests. But coming back to that main theme of uncertainty, I think maps like this for me really help underline that idea that uncertainty is endemic. It's an intrinsic part of geographic information. It's not something you can separate out or sort of treat separately. It really is part of the information. And so it's vital that we sort of show it all together with its uncertainty. And as GI scientists, we talk a lot about imperfection in information. Imperfection is what gives rise to uncertainty, and geographic information is always in some way imperfect. It's imprecise very often, a lack of detail. It's inaccurate. Might have errors, a lack of correctness, and there's a number of other kind of types of uncertainty, types of imperfection, that we talk about, like vagueness, the existence of boundary cases. Okay, so my fourth area was cognition. And to illustrate that, I picked another one of my favorite maps. This is the Wonderground map by Max Gill. And the idea here is it illustrates the importance of cognition in geographic information. It's another transport map, but this time of the London Underground in the UK. It was commissioned in 1913 at a time actually when the London Underground was really struggling both financially and in public perception. It was at the time really only used by commuters, so very heavily used during rush hours and hardly used at all at other times. And the idea behind the map was to encourage more leisure use and for getting around to the theatre or to parks or recreation. And so Max Gill kind of uses this visually striking design to make the map, but also fills the map with kind of jokes and rhymes and whimsy and cultural references and personal experiences. Because of course geography is not just maps, it is experienced by people, and it relates to our human experiences of the world. So this is quite a human personal map of the city, and it was very successful. So it's credited with saving the London Underground, and apparently so popular that at the time there are accounts of people missing their train in order to be, choosing to miss their train in order to be able to look at the maps in the underground stations. And you can see why. It's a kind of riot of colour and a very joyful map that connects you not just to the geography but also to the person. Now, I'll pause here for a moment also to note that all 5 of the maps I've chosen to show you today were created by men, or actually we don't necessarily know that for the Pottinger map. We don't know that it was created by a man. Nobody knows who created it, but it's highly unlikely that a woman would have had access to the opportunities to make a map like that in the 13th century. So I did, and in fact, I should also say that the map Pottinger is named after a man anyway, Thomas Pottinger. So I did naturally think quite carefully about this, and whether, in particular, whether I would seek a historical map by a non-male person to sort of rebalance that story. But I mean, actually, the story is very unbalanced. Maps and mapping, the creation and ownership of maps has always been the preserve of the elite. And that means men and men's stories are represented everywhere, and women's stories are very rarely represented. They're suppressed and obscured by maps. So this is not just a very human view of London, it's also a man's view of London. And that's kind of, I think, important to kind of bear in mind as we're looking at all these different maps. Of course, that entrenched disadvantage of women and people of diverse genders that's despite that, there's still obviously a huge contribution in the field of GI science by women and people of diverse genders, including, I wanted to mention here one of the key people in spatial cognition, Barbara Tversky, who is Professor Emerita at Stanford. And she was particularly influential in shaping our understanding of kind of how humans think about space, those sort of cognitive biases that arise in humans. And there's a couple of examples illustrated here. I'll just talk you through them. The one on the left is from 1978 in a paper by Stevens and Coop, who looked at the distortions in memory in cardinal directions between 2 cities in the US, between Reno in Nevada and San Diego and in California. And in experiments, you can show, it's really quite robust, that people tend to remember San Diego as west of Reno. You can even ask people who live in Reno and San Diego, and they get this wrong. So why would that be? Well, of course, what's going on is that California is broadly west of Nevada. And so people remember that and have a mental shortcut where they go, well, California's west of Nevada, so places in California are generally west of places in Nevada, even though that's not actually the case in many individual instances. But it's a massively beneficial shortcut, mental shortcut that people use in order to be able to reason about space. And Tversky really deepened our kind of understanding of those sorts of effects. She looked at a range of kind of different distortions, both in memory and in cognition. There's another one here that's to do with alignment and rotation. Again, a similar idea. Santiago is remembered as being west of New York City, when in fact it is to the east. And what's going on there is there's an alignment process. People generally think of the west coast of the Americas as sort of being north-south. And indeed, you can even give people these sorts of shapes, and they will misalign the shapes to accord with kind of how we remember it. So those ideas are also really important. That these that these distortions are not just bugs or errors; they're really actually quite fundamental to how we structure knowledge about space and how we reason about space. So my 5th and final map is connected with a historical event. This is the Battle of Fishguard, also known as the Fishguard Fiasco. And it's related to this 5th area of dynamism, representing change and events on a map. And so the story behind this one is that in 1797, a force of about 1,400 French soldiers and irregulars landed near Fishguard, which is in Wales in the UK, in a rather chaotic and botched invasion attempt. things started to go wrong pretty much immediately. There was, desertions and drunkenness and ill discipline. The French force was made up of a large number of irregulars, people who were essentially convicts or press ganged into it. So it wasn't a particularly good start. And a much smaller force of British reservists and locals was hastily assembled to meet the invaders. And in fact, when it came to battle, the French forces surrendered with only a couple of dozen casualties. There was hardly any actual battling. And it's supposed that the French surrender may have come from a sort of misunderstanding of the size of the much smaller British force, possibly because the national dress for women in Wales actually is tall black hats, a bit like sort of stovepipe hats, and a colourful shawl, sometimes a red, and red's the national colour of Wales. And it's thought that, well, maybe the women in the area who came out in force actually looked a little bit like British soldiers, who, if you think of kind of changing the guard at Buckingham Palace, also have these tall black busbies and red coats. So perhaps at a distance, it's possible to make that mistake. And what I love about this map is I think it does really quite an amazing job. It's clearly a static map. Maps are very static, or at least that sort of traditional map metaphor is very static. It actually does a really good job if you spend a little time looking at it and looking at the events and sort of piecing them together. It actually does a really good job of communicating the events and the sequences and how the different events related to each other. There was an invasion fleet landed in the north, and with the ABC, the blue up there, there was an early attempt by the British forces to meet them, but actually darkness fell too early, and so the following day they actually all met on the beach where the invading forces, the French forces, surrendered. So even though we don't actually have interaction here, it does quite a good job of depicting dynamism and events. So I'm going to end my talk, or my final section, having looked at those kind of 5 areas. What I'd like to do is talk a little bit about an example of some of the work that I've been involved in over the past 10 years or so. And I'm hoping to illustrate with that not only some of these ideas, that some of these kind of core expertise, but also how ideas from other disciplines really come in and influence what happens in an interdisciplinary field like GI science. And of course, visualization, Vis, is a really important community for GI scientists, and a lot of those key ideas have come really from this community. So the background to this work is all connected with decision-making in bushfires. And that's obviously a major, wildfires, a major hazard in Australia, and of course increasingly all around the world. In Victoria, whenever a wildfire is detected, it actually immediately triggers a simulation. So there's a emergency preparedness system that the government runs, where the fire is immediately put into a simulation system, and we look at the potentially impacted areas. And you can use that to generate maps like this that show the possible hazard resulting from a wildfire ignition. And in fact, the data behind this map came from that Victorian bushfire system. It's called Phoenix Rapid Fire. And I'd also like to acknowledge one of my collaborators on this paper, Kevin Tolhurst, who not only helped develop that system, but he's a hugely respected wildfire scientist who received an Order of Australia for his work over many decades into wildfires. So a question then is, okay, how do we communicate? Well, what's the best way to communicate this sort of information about risk to people in the community who may need to act on that information and may, for example, need to decide whether to stay and defend their property or abandon it and leave for safety? And that's actually a key decision that's built into how we approach wildfires in Australia, is planning ahead and making good decisions around those sort of stay and defend versus leave decisions. And so I've actually highlighted a particular location here of somebody's, it might be somebody's house, where we might actually ask this homeowner, okay, given this information, what do you think? Do you need to leave or do you need to stay and defend? So to explore this, we used a method from experimental economics, because that's an area that really understands decision-making under risk. That's a key part of what they do. And so I'll also highlight one of my other collaborators, Tom Wilkening from the University of Melbourne, who's internationally renowned experimental economist, and we used his lab and his kind of experimental design expertise for this. And so we developed a range of these cartographic designs, some of them better than other ones. They're all related to actual designs used either in software or in emergency kind of warning communications. So they were picked for that reason. There was 5 maps. There was also a textual description. And what we did is we gave these to participants and asked them to make those decisions. Do you stay or do you leave? Given a large sample, I think it was each participant looked at over 100 maps. A key feature of these experimental economics designs is that they're incentivized, they're performance incentivized. So we looked at if did they make the right or the wrong decision? So if they decided to leave and their property was not impacted, or they decided to stay and their property was impacted, they didn't get any performance bonus. But if they decided to leave and it was impacted, or they decided to stay and it wasn't impacted, then they got that performance bonus. And incentivized experiments like that are really not at all standard in GI science. Certainly at the time, probably still not. And so we were actually faced with quite a lot of challenges getting this over the line for the journal. But I'm very glad we did. I think it was really worth it, because these sort of ideas this is the gold standard in economics for exploring decision making under risk. And I won't go into all of those discussions, but experimental economics has really spent a long time, thinking about these sorts of questions of how do you elicit this sort of information from participants, and they have an awful lot of expertise in that we were able to use. We were able to leverage that. And the difference was especially important to us because I think a lot of previous work has looked at the question of map reading task. Can you deduce, can you read off the map the right value? But I think that's different, or our hypothesis in this work is that's a little bit different from the decision-making task. What actually was the decision you made, and what was the outcome that resulted from that decision? And that's particularly tricky around risk and risky situations, because sometimes you make the rational decision, so there's a very low chance of your house being impacted, so you make the rational decision to stay and defend, but you just get unlucky every now and again. Even though it's unlikely, sometimes the world doesn't end up the way that you expected. So we were particularly looking at that as well. And, that was part of our experimental design is occasionally people who, even if they made the rational decision, might end up with the wrong outcome. And so they wouldn't get that performance bonus in those cases. So again, I won't go into the details, and the paper is there. There's a link on the next page if you're interested in more of those details. But the idea here is that those the results did actually broadly support that sort of a hypothesis that different cartographic designs lead not only to different decisions, sort of systematically different decisions, but also those different outcomes. The performance was different with these different designs. This is just a summary of a logit analysis that essentially summarizes those differences. And there were other things that came out quite nicely of the work if we turn up the difficulty of the task. So for example, with time pressure, we add in not just doing the task with a performance bonus, but we make time part of that performance bonus, then that amplifies the differences in the different representations. In fact, you can go too far. We also added this distraction task. that made it so difficult that then it degraded to becoming pretty much flipping a coin. There was no particular value in any of the different maps. So again, that's kind of useful information when thinking about how these different representations might work in an emergency scenario where, yeah, you will have time pressure and distractions and stressful situations. But my point is really more about that infusion of methodologies from different areas, from experimental economics rather than perhaps the specifics of this particular study. And so my final example, I'm just going to point again to some of those key ideas that have come into GI science. And in this case particularly, I associate them with the Vis community in particular. And just talking about some of the ways that I think they've really impacted the GI science community. And I'd like to highlight one of my other collaborators here, Suzanne Bleich, a cartographer and GI scientist, but indeed a very active member of this Vis community. Unfortunately, she couldn't be here this year because of commitments in Switzerland, but normally I think she would indeed be right here in the room. And I've learned an enormous amount from her, not just about cartography, but also about some of these sort of key ideas from the Vis community. And one of those ideas, for example, is the importance of kind of use of information in context. Of course, those experimental economics design that I talked about just now, we had participants coming into specialized experimental economics computer labs. They would just get to look at their screen. They've got performance incentives. They have to look at like 100 maps, 112 maps, I think each of them had to look at. So really great for generating psychometric data, not particularly great for understanding use in context. And I think that's certainly something that my clear impression is that this community also really understands. And I think in GI science, we've learned a lot from this community around those sorts of ideas. So with Suzanne, I was also involved in some work at that other end of the spectrum at, being more qualitative analysis, in this case, using focus groups. And just to give you a bit of background to some of this work, what you're looking at here is there's a schematic map of the Murray River system. But in the top, there's a picture of a big crane here with a giant log, a dead tree there. And in Australian vernacular, these are called snags, these giant logs. And in fact, this is not taking the log out of the river, it's actually putting it back in. For over 2 decades, water companies spent a lot of time and money removing snags out of the river in order to increase water flow, with the idea that that would help cities and agriculture. It didn't make much difference to water flow. What it did make a difference to was fish breeding, because it turns out that fish really depend on having these in the river in order to be able to have healthy populations and for breeding. So as part of this major project in the Murray River system, the companies were actually at great expense putting these snags back into the river in order to help with fish populations. And of course, when you do that, you can't just look at, in the area that you've replaced the snag. That's highlighted there at kind of regions H, F, and D, the highlighted regions, because the fish migrate around the river. So you have to look at the movements over the whole river system in order to understand is this kind of re-snagging, it's called, actually helping fish populations or not. And so there was this major multi-year project where the river system was actually instrumented with logging towers, radio towers at key points that sort of partitioned the river into different zones. And then a very large number, over 1,000 fish, were removed from the rivers, had radio tags surgically implanted and then replaced in the river. So over about 6 years, they built up this really interesting picture of the movements of fish around this river system. And the main point of that was to show the impacts of re-snagging. But actually the fish ecologists knew that there was so much other data in there. They were desperate, really keen to get at some of the other patterns that were there, but didn't quite know how to do that. So that was kind of part of what Suzanne and I and the team worked with them on. And we looked in particular at overview visualizations, giving them, usable pictures of all of the movements as a sort of preliminary to exploratory data analysis, actually looking at, how those movements, what different ways of how we can represent this kind of movement of over 2.5 million fish movements in this quite complex scenario. And what we were really looking for was insights. We were looking for those kind of key insights. And that, again, to me, is an idea that's very much come from this community. It's one that's really, become quite important in GI science. But I think the expertise from this community in kind of, the importance of insights is something that's really had a big impact in GI science. This was just one of our very basic overview visualizations. It was on a big sheet of paper, an A3 sheet of paper. The colors were not particularly our choice. They were actually the colors that the fish biologist already used before we arrived. But the idea here is to show the locations, the colors relate to zones, and each line relates to a fish, and so you can see where they've moved over all this period of time. And then ask the question, well, when you get a room of we had 4 groups, some of them expert, some of them novice groups, and looked at the discussions that they have, qualitative analysis in the focus groups to see to what extent did the different visualizations in the different groups form interesting insights about the data. And I'll just show you this another one of the 4 representations. We use this as a sort of schematic spatial representation where for each region you can, I've got the blow up shows you some of the detail there. You can see where the fish that were detected in that region moved to. So, and actually one of the things you may notice immediately is that some of the regions that they move to from D are not necessarily the adjacent ones. That's a result. Sometimes fish are able to sneak past the radio transmitters, so they don't always catch them. But there you go. That was immediately kind of the sorts of insights that come out potentially of approaching data in this way. So that's really all I wanted to say. I guess hopefully I've kind of convinced you that perhaps there is this intersection of expertise in GI science. But I think the more important point for me is reflecting a bit on the way that other ideas have come into the field that I'm part of. And, I really hope that resonates with researchers here, because, I think the visualization community, the Vis community, has been and continues to be a really important part of that evolution. And, I see an awful lot of interdisciplinary work going on here. So I hope that's been useful to listen to, but thank you so much for your time and attention.